All right, let's get started. We're going to be solving LeetCode's Biweekly 117. Let me share the link in chat. Hey, thanks for the follow, the great Fonsby. Thank you. All right, so let's get going. So let's start with question 1. Let me share the link for the question. So it's called distribute candies among children, number 1. So there are two, question 1 and question 2 are similar. What language you use? I use Python. But I can use, I know other languages. So you're given two positive integers, n and limit. Return the total number of ways to distribute n candies among 3 children such that no child gets more than limit candies. Would you recommend learning C or Python first? I would recommend Python first. C is more difficult. With Python, you can avoid they're more it's more abstract. You don't have to get into the details of dealing with pointers. So I would start with Python. Also, C is not, unless you're going to be doing some low-level programming, I would not recommend you go in the C route or the C++ route. Anyway, so yeah, let's do this. So here we have 5 candies, and we can give up to 2. There are 3 ways to distribute 5 candies. So here we get the 3 ways. So 1 to the first child and 2 and 2. So notice that you have to, you can't have leftover candies, right? So here there are 3 ways. And notice that we're not giving 3 or more because the limit is 2. Here the limit is 3 and we have 3 candies. So we have more options. We have 10 options, and here they are enumerated. So this is a very concise notation for the, so these are triples, and the first element of the triple is how many candies the first child gets, and so on. So it's good that they give us this way of thinking about it. So yeah, so here the limits are the constraints are pretty small. So n is up to 50, and the limit is up to 50 as well. So okay, so what can we do? So we can first consider how many candies we're going to give to the first child, right? And what do I mean by consider is that we can just loop over all the possibilities. So we have, so let's call it C1, the candies that child 1 is going to get. So it can have between 0 and the minimum for the minimum between n. He or she can have more than n because that's how many there are, and limit the minimum of those. And since and we want this to be inclusive in Python, so we add 1. So now we are considering, so now we have a specific value of C1 that we want to consider. So notice that even though this range is potentially valid. It could be that it is not, right? Because, for example, if we give 0 to the first child, then maybe we have too many for the other 2 children, and we will not. For example, if we have here, notice that the 0 to the first child is not an option here, because if we give 0 to the first child, then we are left with 5. And that means that we will exceed the limit of the other 2, right? Because if we can give up to 2 to each, and that adds up to 4, but we have 5 to give them. So that means that not all of these values are going to be valid. So how do we know if they are valid or not? Well, let's do the same for the second child. So here we also want the minimum between how many there are and the limit, right? So this is similar. The only question is how many there are depends on how many C1 got. So this is going to be the total minus how many we give to child 1. And now we're done, because the remaining, so C3 must be whatever is remaining, right? Which is this expression. However, there could be a problem, because maybe we're given C3 more than the limit. So only if C3 is less than the limit, we want to count this possibility. And this should give us the answer. And notice that this is fast enough because we have 2 loops. So this is going to be 50 times 50 squared iterations at most. And that's not too many. That is to 2,500. So that is fast enough. So let's run the examples and we get the right answers and we get accepted. Cool. So I noticed that some people wanted to do this recursively. And of course you can. And actually, this is what you would do if the number of children was a variable. It was an input of the problem. So you could, so we could count, and we're given, we could have a recursive function. And we're given the amount of candies and the amount of children that we want to distribute it. And so if there's only one child, then we have to give him all of them. But also we also want the limit. But if we give n of them, but only if the amount remaining is less than or equal to the limit, we have found one solution, one way to distribute the candy. Otherwise, this is not a valid way. And then we want to go from we want to go from, again, from 0 to the minimum between n and limit. And for each of them, we want to count, but we have to subtract the ones that were given to the current child. And we now have one less child, and limit is always the same. So we want to add all the possibilities for that. And so this would be our recursive function, and here we just want to return the let me save the submission. So, and here we want to return just the count for n candy, 3 children, and with that limit. And again, we get the right answers for the examples, and we also got accepted. So yeah, this would be the recursive way of solving. Let me share my submissions in case you want to check them out. So this is the iterative, and this is... So notice that this is a kind of backtracking. If you think we're doing a brute force, we're considering all the possible. We're not caching because it's not necessary. We could cache this. We could cache this here, and that would be memoization. But this should work because it's just the same. But because we would have some overlapping subproblems. Because if we distribute the candies for the first and the second childs in ways that are that add up to the same, then we're going to end up with the same final call. So we're gonna cache it, but it's not really gonna make a difference because we have only one. So it is O of 1 to solve the case where there's only one child, so it's not worth it to do the caching. But my point was that this is, you can think of this as a backtracking solution, and you can always do this when you have a fixed and a small fixed number of choices. Then you can always do nested loops for it, or you can do it recursively like we did here. Okay, so let's move on to question 2, which is the same problem, but this time we have up to 10 to the 6 candies and up to 10 to the 6 limit. So here we cannot do the 2 nested loops because that would be 10 to the 12 iterations, so 10 to the 6 squared, which is a lot. It's too much. It's going to be too slow. So, but we can have one loop, right? We can have again the same thing. Let's copy it. Why not? Your stream keeps going from making it very blurry. Can you fix this by any chance? Well, that's thanks for letting me know. I don't know how to fix this, but I'll research later. If you have any suggestions, I can try them out. Otherwise, I'll look into it afterwards. Okay, so what I was saying is that we can do the same for the number of for the number of candies for the first child, but now we cannot do a loop, so we have to somehow think of what are the valid ranges, possible values for C2. So notice that for we know that C2 must be less than or equal to the limit and greater than or equal to 0. That's obvious, but and we also know, well, not only this, but we know that it cannot exceed. So this is the loop that we have, right? So this is L, but also n minus C1, right? So this was our loop, but then we had an if statement so that we didn't have too many left for C3, right? So that means that we could have, if we give C2 too few candies, then we might have too many for C3, and C3 would exceed the limit. So one way to think about this is to notice that C3 must also be less than or equal to the limit, but C3 is n minus C1 minus C2, right? So these two inequalities are equivalent, and now we can change this so that we can isolate C2, so we pass C2 add in here, and then we have n, and we subtract L from both sides. So now we have a lower bound for C2, right? Which is this. So that means that C2, again, we have the upper bound. I'm just repeating what's there. But now we have an upper bound, a lower bound, which is this number, but also 0. So we want the maximum between 0 and n. So all the elements in this range are valid C2s, in the sense that they will leave values for C3 that are also valid. So we just count how many there are, how many integers there are in this range, and we'll get the answer. So we had the upper bound was something, was a minimum, the lower bound was a maximum between 0. So this was the usual n minus C1 and limit, and this was n minus C1 minus L minus the limit. And since we are including both extremes of the range, we need to add 1, and this should give us the answer. So we get the right answer for the examples, and we got a wrong answer. Did I copy this correctly? The minimum between let me check. Let me check. Check this real quick. This is the contest. So we also want C1 to be So yes, there is another condition that we want. So this is how many are remaining. Okay. Yeah, so this condition is that whatever it is remaining from after we've given the candies to C1 has to be less than 2 times the limit. Because if it's greater than one of the remaining children, will have to have more than the limit, which is what we discussed in Q1. All right, so let me share my submission. Following along, no worries. Just started learning Python, so I appreciate the breakdowns. That's great. Yeah. So, well, now that you say this, maybe yes, we could do this in a more Pythonic way, in a one-liner, by using the sum function. So you can usually do this mechanically. And yes, this is another way of writing the same code, the same algorithm. Okay, so let's move on to question 3. So number of strings which can be rearranged to contain substring. So I'm still thinking about this, because yes, here we can, so yes, this what this means is that, so we started C1 from 0, but there is such a thing as giving C1, so as giving the first child too little candies, right? So we can express this. So if we have this expression, we can change it by moving C1 to the other side and 2 times the limit. So this is equivalent, and that is giving us a lower bound for C1. So instead of having the if statement, we could have this here. So yes, so the error was to, so I considered all the values for C2 given the C1 value, but there were some C1 values that were not valid. So that was my mistake. And yes, this is a better way to do it because we are not going over invalid values of C1 and then filtering with an if statement, which is going over directly over all the valid ones. So let me give you this other submission as well. So we're breaking it down pretty thoroughly. So number of strings which can be rearranged to contain substring. Given an integer n, string s is called good if it contains only lowercase English characters, and it is possible to rearrange the character of s such that the new string contains leet, L-E-E-T, as a substring. So for example here, so yeah, notice that it doesn't have to be a substring. Well, it says that you can rearrange it, so it doesn't have to be a substring. It could be, so if you have at least one L, at least two E's, and at least one R, then it is going to be good. So return the total number of good strings of length n. Since the answer may be too large, return it mod. So, okay, let's write down the mod before we forget about it. So this is the usual number. And so here we get all the answers. And here we get a big number. So we get what the number is before the mod. And this is after. This is what we have to return. So that's good because if we forget to mod, we should get a wrong answer here for example 2. And n is up to 10 to the 5. Okay, so yes, here, so one approach would be to start generating the string one character at a time from left to right, and we have a choice at each point. So for the first character, we can choose any of the 26 lowercase English letters, right? So we have 26 choices, and then for the second one we have 26 choices, and so on, and all these are independent. So this is kind of a take it or leave it kind of problem, where we can use the P because we're gonna have repeating subproblems. However, there is a catch, which is that we want to know if we already contain leet in the string that we are generated or not. Because at the end, when we have generated the whole string, we need to know if it's good or not. If it has leet, if it has at least one L, at least two E's, and at least a T, right? So we can extend the subproblems by remembering how many of those 3 letters we added, and that will let us know in the end if it is good, right? So we're gonna cache it and we're gonna count how many there are, given that we have n characters to fill, and we want to know how many occurrences we have of each. How many we have to add. So if we don't have to add any more letters, then we need to check if we don't have any remaining L's to add, or any remaining E's or any remaining T's. So if that is the case, so we want all of them to be 0. If that's the case, then we found a string, otherwise we didn't. And here we have, so the next character could be an L, could be an E, could be a T, or could be something else. We don't care what the other choice is. So here, if it is an L, we subtract 1 from L, and if it's an E, we subtract 1 from E, and if it's a T, we subtract 1 from T. But notice that we don't want to have a negative number of L's, because otherwise we'll have too many subproblems here. We'll have too many possible values for L, too many possible values for E, and so on. But we don't care if we added 1 L or 2 L's, it doesn't matter. We only want to know if we added at least 1. So that means that if we get to 0, we just stay there. So if we do max between these and 0, we'll stop at 0. And then we have the other case where we add another letter. So the counts of L, E, and T don't change, but we have 23, so there are 26 characters in total, but we have considered L, E, and T, so the remaining are 23. So, and now we have to mod, and we return it. And so we want to count how many there are that have n letters, and we need 1 L, 2 E's, and 1 T. So this should be it. We get the right answers for the examples, and we get accepted. Let me share the link to my submission, and let's move on to the last one. Here's the link. So maximum spending after buying items. It's weird that you want to maximize your spending. Well, I guess if you are the seller. Anyway, so yeah, this statement is a little complicated. So yes, you have an integer matrix values that has m rows, which are shops, and n columns, which are items that the shop sells, and the value in values indicates the price, or well, the value of the item, and they are sorted. So they are sorted, so you have these conditions that every row goes from largest to smallest, and on each day you would like to buy a single item from one of the shops. So in the dth day you pick up a shop and you buy the smallest value that you haven't bought yet, and the price that you buy it for is the product between the day number and the value of that item. And you want to maximize the amount of money that you spend buying all the products. Okay, so here we have examples, and well, notice here it is important that there are only 10 shops, so 10 rows at most. Always pay attention when there are some suspiciously small numbers. They are 10 to the 4. So yes, so the product of these two is 10 to the 5, so that's the total number of values that you get in the matrix. Yes, it turns out that it's not really important. This number is not really important, but in any case, it's good to pay attention when there are suspiciously small numbers, because probably you can get away with something, some brute force or some inefficient algorithm. And the values are up to 10 to the 6. Okay, so notice that we are going to we're going to be buying these products in some order. So we're going over all the elements, and we are multiplying by 1 first, then 2, then 3, and so on. And we're adding all those values, and we want to maximize that expression. So let me first explain something. So suppose so forget about the restrictions. Let's say that we have some values. So let's call them B1 up to Bn, right? So these are integers, and we want to pair them with the numbers from 1, 1, 2, and so on up to n. So this is essential. Well, this is a generalization of what we are asked to do. There are other conditions, but let's simplify it for now. So notice that. So let's say that we want to choose the value that we are going. So let's say that this, without loss of generality, let's say that we have like B1. So we sort them in a way so that this is true, and we have Vn minus 1 Bn. Okay, so let's start pairing values. So if we have n, we want to. So you can think about it in terms of money, which makes it more intuitive, but we want to take n times some of these products, some of these values. right? So which one? So n is the maximum that we can get. So then we're gonna get n minus 1 and so on. Well, 3. So which one should we get? If we can get n of them, well, let's take the maximum, right? If we're gonna get n of them, let's get the maximum. So let's pair this with this one. And then if we can get n minus 1, which is the maximum we can take after we have already taken the n value, then let's get the second maximum, right? So and so on. So every value will be paired with the corresponding value in this order where they are both sorted. So you can prove this by thinking, so what if, I think this is intuitive, but if you wanted to prove it, you can say, well, let's say that we don't choose the maximum for n. Let's say that we choose something smaller, but then we are going to pair the maximum value with some other. So you can reduce this to two values. Well, two pairings, and then you can prove that if we switch them, you're gonna get a better, a higher value, and that's how you prove this mathematically. But let's say that this is intuitive. So how do we use this to solve this problem? Well, it turns out, so we just proved that the best order would be to multiply for day 1, multiply with the minimum of the entire matrix, then for 2 for day 2, then the second minimum, and so on in that order for the entire matrix. But notice that here we can achieve that order, because since all the rows are sorted and we're going from minimum to maximum, then we can do a merge. We can get the minimum of the last column and then advance that one, and then get the minimum of the ones of the minimum of each so far. And that is effectively a merge, an n-way merge of the entire of all the rows, and that is going to give us the sorted list of the entire matrix. So we can do this greedily by doing an n-way merge. So that is the key to solve this problem. So how do we do an n-way merge? Well, the most effective, efficient way of doing it, and I think it's easy to implement, is to use a heap, so that we quickly get the minimum. So in this case, since there are only 10 rows, you don't need this. You can do a sequential search to get the minimum of each row, of all the rows. But we're gonna do it here with so let's use R and C of rows and columns. So this is going to be this, and so for the day D, so we want the days to go from 1 up to R times C inclusive. That's how we do it in Python. And we're gonna keep track. We're gonna keep track of the we're gonna keep a heap. Let's call it H, or well, let's call it heap if you will. And so initially, for every row, we're gonna add heap. So heap q. This is how you use a heap in Python. So heap, and so we are gonna add for everyone the minimum element, which is at the end. This is what we are. So this is for the row R. The last element is the column C minus 1. And then let's add the coordinates of that element in a triple, so that we know where it came from. So here we added all the rows. So now we want to choose the minimum of it. So this is the value, this is the row, and this is the column, and we pop from the heap. So this is the minimum value so far. We are going to add that to the result. So the value times a day. And now, if there are more elements, which means that the column is not 0. So since we are going from the largest column to the smallest column, the last one is 0. So if we haven't reached the end, we're going to add that row again to the heap. But with the next element, which is values of R, C minus 1, R, and C minus 1. And this should give us the answer. Okay, it works. And accepted. So yeah, this one was on the easy side of a hard. So I think it had more users accepted than question 3. Yes, so a lot more. So yes, it all boils down to this, understanding this, that you want them in sorted order. That's going to maximize the value. So notice that, like I said, you don't need to use the heap if you don't want to. So here I could do a loop and find what the minimum is. So yeah, let's try that. So for each of the rows, we have the current index of the column, which is C minus 1 initially. And here we want to find the best row, which is going to be the one with the minimum value. So for all the rows, we want the values of, so yeah, let's call this R. So for this value and the current, yes, this is right, but I think we need to also filter So how do we do this? Well, I guess we can add so if the index is not none, the index of the row R. Right. So this is going to give us the best row, the row with the minimum value. So that's going to be values of R, and yeah, let's call this col, not just index. So the column for the row is this one, and now we want to update. Well, not. So this is if it's greater than, so yes, because we're gonna get -1. So if we subtract, so here the so the column now for row, it's going to be 1 less, and when we finish a row, we're gonna get -1 there, so we can filter those this way, and I think this should work. Okay. Yes. Cool. So yeah, this is the way to do it without the heap. So okay, we've solved it. Well, let me share. I didn't share this one, the one with the heap. Cool. So yes, I think that's all I have for the contest. I hope you learned something from it. We went over a lot of options for doing the problem, so I hope you liked it. See you in the next one. I'll try to do another one for the weekly. This was a bi-weekly, but yesterday there were 2 contests, so I'm gonna be doing another stream for the weekly, the one that was last night. So see you in the next one. Bye bye.